Welcome back to K11 Tech University. In our last explainer, we really dug into bit shifts and how they can supercharge arithmetic operations. Today, we're going to tackle a problem that seems almost deceptively simple, but, as you'll see, it opens up a whole world of powerful algorithmic thinking. The question is just that. You've got an integer, how many of its bits are flipped to a 1? In the biz, this is called the population count, or just Popcount for short. Now I know what you're thinking. It sounds like a basic counting exercise, right? But believe me, how efficiently we can do this has huge ripple effects across pretty much every field of computer science.
So why do we care so much? Well, this one little operation is a fundamental piece in so many systems. When you're dealing with security, it's used in permission checks to see how many permissions a user has active. In data science, it's a workhorse for cryptography and data compression. And even in AI, it's used in telemetry to get a read on how dense the active states are in a neural network. Basically, it's a super fast way to ask how much of this thing is on right now.
All right, so how do we actually solve this? Well, the most obvious way, the one that probably pops into your head first, is what we'll call the naive approach.
It's exactly what it sounds like. You just loop through every single bit in the number, one by one, and if you see a 1, you add to your counter. And look, this totally works. It's perfectly fine if you're only doing it once in a while. But in the world of high-performance computing, where an operation might need to run millions or even billions of times a second, this simple loop becomes a massive performance killer. We need something better.
And better almost always means more clever, right? This leads us to a much more elegant solution, Brian Kernighan's algorithm. This is a real classic, a bit manipulation trick that every serious programmer really ought to know.
Here's the core idea, and it's brilliant. Instead of checking every single bit, what if the loop only ran for as many times as there are ones? That's what this algorithm does. So if you have a huge 64-bit number, but only 3 of those bits are set to 1, the loop only runs 3 times. That's a huge efficiency gain, especially for numbers that are sparse, with lots of zeros. So how does it pull this off? It's all in this tiny loop. You start with your number, which we'll call n. Now the magic is in step 2. You do a bitwise AND between n and n-1, and you save that result back into n. Then you add 1 to your counter. You just keep doing that until n becomes 0. The whole trick, the real secret sauce, is what's happening in that second step. Let's break down that bitwise operation. Anytime you subtract 1 from a binary number, something really predictable happens. The rightmost 1, what we call the least significant set bit, it flips to a 0. And at the same time, every trailing 0 to its right flips to a 1. A perfect example is going from the number 8, which is 1, 0, 0, 0 in binary, to 7, which is 0, 1, 1, 1. See that pattern?
Okay, so that brings us to the next step. When we perform that bitwise AND between our original number and our new n-1 version, everything to the left of that bit we just flipped stays the same. The flipped bit itself is now a 0 in the n-1 version, so the result there has to be 0. And all those trailing bits that were zeros in the original number, they also result in zeros. The end result is that we have surgically removed exactly one set bit, the rightmost one. It's just a beautiful, elegant use of bit logic.
Now, as slick as Kernighan's algorithm is, modern computing has an even faster trick up its sleeve, leveraging the hardware itself.
You see, most modern CPUs have a special instruction, often called Popcount, baked right into the silicon. This is the absolute peak of optimization for this problem. It gives us constant time bit counting, which means it takes the exact same tiny amount of time no matter how many bits are set. Because it's happening at the hardware level, it's just orders of magnitude faster than any loop you could write in software. A lot of high-level languages actually give you direct access to this, and for any code where performance is critical, this is the way to go.
But hold on. If there's a hardware button that just does this for us, why did we spend all that time learning Kernighan's algorithm? That's a fair question. The answer is all about the algorithmic perspective it gives us. The real lesson here isn't just about counting bits, it's about a way of thinking.
And that brings us to what I think is the most important idea in this entire explainer. Popcount isn't really about counting at all. That's just what it does on the surface.
The real difference is in the mindset. The naive way is what we'd call looping blindly, just grinding through every single bit, whether it's a 1 or a 0. The more elegant approach is about exploiting structure. It takes advantage of the built-in properties of binary numbers, that trick with subtracting 1, to find a much smarter, more efficient way to get to the answer.
What this problem really teaches us is to think deeply about how our data is represented.
It forces us to consider the density of the information we're measuring and to invent clever ways to iterate only over the things that actually matter. That right there is the heart of great algorithmic thinking.
Okay, so let's bring this back down to earth for a second. How does this actually show up in real-world code, and what are some of the common traps people fall into?
You'd be surprised how often you see a slow, naive loop dropped into a part of the code that needs to be incredibly fast, where it just becomes this huge bottleneck. An even more common mistake is simply not knowing that your programming language or CPU already has a super optimized popcount function built in. Real efficiency comes from knowing your tools inside and out, not from just guessing. And you'll find this idea everywhere once you start looking. It's used in operating system schedulers to juggle process priorities, in complex graph algorithms, and it's famous in the world of chess engines, which use something called bit boards to represent the game state in a way that's incredibly fast to analyze.
The big takeaway here is that this tiny, low-level operation, just counting ones and zeros, can directly shape the high-level behavior of huge, complex systems. It's an amazing concept. It truly scales all the way up from bits to behavior.
So where do we go from here? Well, in our next explainer, we're going to build right on top of this foundation. We're going to take a step up in abstraction and explore how we can use these bit-level tricks to efficiently manage entire sets and subsets of data using bit masks. It's a really cool bridge into even more advanced algorithms. This has been K11 Tech University. Just remember, sometimes the smallest, most fundamental operations, when you really understand them deeply, stop being simple tricks and start becoming incredibly powerful tools in your arsenal. We'll see you in the next lecture.